All right, you guys, so we're going to go over chapter 14, redox. Now, chapter 14 feeds off of chapter 6. Okay, so in this case, we're going to be talking more about those chemical equations, breaking them apart and whatnot. Something that we left off on chapter 6 was the sound that lions make, right? So, lions or a Leo, when it wants to communicate with something, it constantly goes, right? So, Leos they grr, right? So Leo's grr means lose electrons, you're oxidized. Gain electrons, you're reduced. Okay, so that's a quick way of remembering our redox equation. So you're gonna lose electrons, then that means you're going to be oxidized. And if you gain electrons, right, you're more negative. That means you're going to be reduced. So when you lose electrons, you're more positive. So you're more positive. When you gain electrons, you're more negative. And if it helps you to make a number scale, right? Actually, it's going to go continuous. Okay, this is 0, and let's just say -1, -2, -3, +1, +2, +3, right? So as you're moving around, if you're in this area and your arrow is moving more towards the positive side, then you're being oxidized. Okay. Now, if your arrow is moving the other way, if your arrow seems to be moving this way on the number line, right, then you're going to be reduced. And so if you start off with something that's a +2 and you end up with a -3, you're reduced. Or if you're a +2 and then you go to a 0, that tends to confuse everyone is when you're at the 0 state. You're like, well, what happened? So how did your number line move? Did you start here and end over here, here, or here? So are you oxidized or are you reduced, right? More positive or more negative. All right, so here are a couple of rules for our oxidation states. Actually, I shouldn't say oxidation, for redox. I'm going to call this redox. Rules for redox and figuring stuff out. Okay, number 1, any elemental form is going to get a charge of 0. Okay, so any elemental form, you're going to get an oxidation state of 0. Okay, so the examples we have, this is kind of like oxygen, right, by itself, sodium metal by itself, bromine by itself, okay? Even though they're diatomic, these two are diatomic, they're still an elemental form. That means it's just that single element. They're going to get an oxidation state of 0. Number 2, monoatomic ions. Okay, so this is going to be on monoatomic ions. So this is ions by themselves, single atoms, right? Their oxidation state is going to equal to the charge. Or the oxidation charge. is equal to the actual charge of the ion. So the example I have here is going to be chlorine. If chlorine loses an electron and gets a -1 charge, so its charge is -1, and its oxidation state is also going to be -1 in its aqueous state. So ions are usually found in aqueous states, okay? So an aqueous state. Number 3, polyatomic ions. So that means ions with more than one atom, okay? So let's get a different color here. Your oxidation number must add up to the overall charge of the ion, right? Or of your compound that you have right there. So it must add up to that overall charge, okay? It's going to be 0 for any neutral compounds. Now, what we mean about this one right here, so let's go ahead and describe this one, is if we have a compound like SO2, okay, or SO2 with a -2 charge. Let's actually put the example down here. So if I have SO2 and SO2 with a -2 charge, and I want to find out the oxidation numbers of each of these. So usually we write it on the top, but I didn't have enough space for the top of it. Oh, my camera's like not cooperating right now. There. Nope, keeps falling. All right, so let me just do it on a separate page because it's not going to stay. It keeps falling. Okay. So we're going to have SO2 and SO2 with the -2 charge. Those are going to be the two that we're going to look at. So the first one right here has no charge, nothing in it, right? So let's go ahead and figure out what the overall charge of this one is going to be. We know it's neutral, but what is it? All right. So sulfur, let's figure out. Actually, let's look at the periodic table. I don't want to give you guys a wrong thing for sulfur. Dun, 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 dun. Sulfur has 6 valence electrons on it, okay? And that means it can make a charge of 2, right? So let me continue to look at I didn't look at the periodic table, I just looked at I Googled it, and I shouldn't do that. I should actually confirm with a periodic table so I don't get confused. All right, sulfur and oxygen are exactly the same. They're both in group 6A. Okay, there we go. Here's sulfur, and here's oxygen. They're both in group 6A. Okay, so that means they each have 6 valence electrons. That means they can both make a -2 charge. Okay, all right. So starting with this one here, because sulfur is going to be one of those that we're quite not sure what it's going to be. It's one of those exceptional ones, but oxygen doesn't change. So we know oxygen's a -2, and there's 2 of these. Okay, so there's 2 of them. So we're going to have a total of a -4 charge here. In order to balance this -4 and get a total charge, so this is going to be my total charge of 0 because it's neutral, sulfur has to be a +4. So +4 minus 4 is going to equal 0. So my total charge is going to be 0 for this one. And when I find out what the oxidation states of them are going to be, well, we would write them like this, right? Like this one has a +4, this one has a -4. But if we're talking about the polyatomic ion in total, it's going to be a 0. Now let's look at this one right here. Okay, we said oxygen is -2, and there's 2, so that's going to be -4. So -4 something here plus -4 has to equal -2, right? So you got this equation here. X plus -4 is equal to -2. Well, to solve this problem, you're just going to bring 4 to the other side. So now you're going to have X is equal to, when you move 4 to the other side, you're going to actually have to add 4 to both sides, right? So 4 minus 2 is going to be a positive 2. So now you'll notice how the oxidation numbers have changed for the sulfur atom in both of these cases. However, the polyatomic ion, which is the whole thing, in this case, this whole thing has a charge of 0, it's neutral, and this whole thing has a charge of -2. It's given a charge of -2. Now, if it wants you to find the actual charges of them individually, that's what we just did here, where this sulfur has a charge of +2, and this sulfur has a charge of +4. All right. Let's go on to the next one. Next rule number 4, is going to be atoms and molecules or polyatomic ions get an ionic charge. So here's our example. Hydrogen, and I believe, don't quote me on the name of this one. It's probably chlorate or hypochlorite. I'm not sure. Okay, I would have to look at the polyatomic ion chart, which I said it's okay to do to figure out what it is. Anyways, we want to figure out the charge of the whole thing. And in order to do that, we know that this is neutral. There is no charge indicated here, right? So whatever this is has to equal 0. I know that hydrogen is a +1. So that means a +1 plus whatever this is has to equal 0. So this tells me that the charge of this one is going to be a -1. Okay? So these ones right here are ionic charges. So if this breaks apart in an ion, it's going to have +1 for the hydrogen, and this ion is going to be a -1. And you notice I'm putting aqueous because this is assuming that we're in the solution when it breaks apart into a solution. Okay. All right, let's do an example with an equation in it now. Okay. I'm like scared of moving my camera. I want you guys to see this. Okay, hopefully it doesn't move and the angle isn't like too bad. Okay, so let's continue this. Let's get an example of sodium plus water, liquid water. And this is going to be sodium solid. Gives me, what is it going to give me? I don't know yet. All right, so here's an equation. We want to dissociate this equation. And remember, to dissociate means to break apart its atoms inside of water. Now, sodium is going to react with water. It actually reacts kind of violently with water. It creates fire and tiny little booms and explosions with it. Tiny, tiny, tiny. Mainly the fire, it's causing that. So sodium inside of our water, what's it going to happen to this? Well, you're going to end up with some sodium aqueous, right? and we're going to end up with the broken apart water molecule as well. Okay. Now remember, hydrogen is diatomic. It's going to come on its own. All right. So this is kind of what we ended up with. Now we have to finish this because obviously it's not completed. It's not anywhere near done. We have to balance it. We actually have to figure out the states of matter. So solid sodium combined with liquid water is going to create an ionization, and we see that they broke apart. So in this case, we get sodium in aqueous. Hydroxide is also going to be aqueous. And this hydrogen, diatomic hydrogen, whenever you see your diatomic molecules like this, be kind of wary. Find out its natural state at room temperature. H2, hydrogen is actually going to be gas unless they state otherwise. That's what you're going to get. Okay. All right. Now we want to associate what kind of ions or charges these are going to have. Right? So a sodium metal by itself, this is elemental and it's a solid, so we're going to give it a 0. Okay. Sodium aqueous ionized, and it's going to get a +1 charge. It's in group 1 of the periodic table. Hydroxide is a polyatomic ion, and I've memorized the charge of this polyatomic ion, and that is -1. Hydrogen is elemental, so it's in an elemental state. So it's going to have an oxidation state of 0. Okay. Now, we're going to have our liquid water right here as well. Okay, so liquid water is kind of tricky. We sometimes give it a 0 and sometimes we count it. We're trying to see what's happening with these. Okay. Let's go ahead and just break this one up apart. Right. So we know that oxygen's a -2, and we know that each water is a +1. So let's figure out what's going to happen with this one. Right? Sodium metal has gone from a 0 to a +1. Hydrogen went from a +2 to a, well, here we have a 0, and this one's a hydroxide, and this hydroxide has a -1 charge. We have to figure out what the overall charge is for this one. So it's going to be -2 plus whatever is going to be that, which is going to be 1 for hydrogen, is going to equal to -1. So it's just the -1 charge right there. Okay. And then let's look at oxygen. Oxygen went from a -2 to a -2. Okay. And let's see what happens. When you go from a 0 to a more positive number, right, we're more positive. What has occurred? So you're more positive. We went from a 0 to a 1. We became oxidized. So sodium is oxidized. Hydrogen went from a +2 to a -1. Did I write that correctly? To a +1. No. From a +2 to a +1. Okay. So here's +2, and now it's going down this way to a +1. That shows me that hydrogen was reduced. Oxygen went from -2 to -2, so it's no redox. Nothing happened to our oxygen on this case. So the only ones that were oxidized or reduced was our sodium and our hydrogen in this case. Okay. Yeah, oxidized, reduced, no redox. So quite simple with that one. The only thing we forgot to do with this one is balance the chemical equation. So we have 1 sodium, 1 sodium. Let's see. I like to do the ones that are by themselves last because I could always make these numbers match. All right, let's look at hydrogens. 2 hydrogens here, but I have 3 on this side, right? one oxygen here and one oxygen there. I still need to make them match. So the best way to do it, I'm going to put a 2 here because obviously 1 didn't work. That's going to give me 2 plus 2 is 4. I'm going to put a 2 there. Now I have 4 hydrogens on both sides. I have 2 oxygens, 2 oxygens. Everything else is going to be a 1. Now my equation is also balanced. Let's go and try another one. Okay. So it's going to be a little practice. Determine if the reaction will occur. Write and balance the equation. If no reaction, right? No reaction. Okay. So if you have no reaction, we're going to go ahead and write no reaction for these. So our first one is going to be potassium plus lithium. Our second one is cobalt solid plus zinc aqueous. And this one, our potassium was a solid. And anytime we see anything with, actually, we'll go through that in a little bit. And we'll do one more here. Aluminum plus chromium chloride. Yes. Solid. All right, so all of our metals are going to be solids. Now we have to figure out if this reaction occurs or not. And you're going to go, what? How am I going to even figure that out? Like, what are we talking about there? So there is a table that we're going to actually have to use, and it's called the activities series table. And I'm going to open that up. Dun, dun, dun. Just find a quick little table online. They all kind of work very well. All right, open a new tab. Oh, see if we could zoom in on that. This is a very small table. It doesn't have lithium on it. We want one with lithium. Here's this one's better. Now the reason I'm looking for one with lithium is because we have an example here with lithium, but this would work as well. But I'd rather show you guys the one with what we have. Okay. All right. Here is an activity series or reactivity series, whichever one you want to call it. Now, what this basically represents is the order in which things react, from the most reactive to the least reactive. Okay. Now, in our activities, what we're going to have is what's going to react and what isn't going to react. If you're on top of something in that activity series, you can replace it. But if you're below it, you cannot replace it. So let's look at this. Lithium is in the top of the list. Okay. And we want to know, is potassium able to react with lithium? Okay. So lithium is number 1, and we notice we don't see potassium on here. They didn't put it on the list. But potassium is actually below lithium, right above sodium. Okay. So what that means is that potassium solid, your potassium solid, cannot react with lithium, and this is lithium that's aqueous. The reason I know lithium is aqueous is because it has a charge associated with it. So it's going to have a charge, and this is going to be called an aqueous charge, right? So potassium cannot replace lithium inside of this solution. So there's going to be no reaction. All right. So potassium, like I said, it's going to be down here somewhere. All right. Above calcium, but below lithium. Now let's see if the metal of cobalt can replace the metal of zinc inside of the solution. Remember, these are aqueous, so that means they're inside of solutions. These are solid pieces of metals that we're throwing in the solution and going, I hope it reacts. All right. So let's find cobalt. Here's cobalt, CO. And we're going to find zinc. If cobalt is above zinc, it will replace. If it's below zinc, it won't replace it. Zinc is above cobalt, hence no reaction. These are quite simple. I like these. All right, next one is aluminum and then our chromium. Will aluminum replace chromium or chrome? All right, here's aluminum and here's chromium, right? Aluminum is above chromium, so we are going to actually have a reaction that's going to occur. So let's write down our reaction. Now, if we recognize the type of reactions that we have a single atom and a compound. So we have an AB plus a C. So what happens with an AB plus a C? The home wrecker comes and it's going to replace this. So aluminum is going to replace chromium in this single replacement reaction. And you're going to end up with aluminum chloride. All right, so it's aluminum chloride plus chromium. Okay. Now we also have to figure out the states of matter of these. Aluminum chloride reacted, so it's going to be our aqueous. Chromium doesn't really react on its own. It got separated, it got kicked out. It's the precipitate. This right here is called the precipitate. Precipitate. Okay, it's the solid that form. Okay, the precipitate. Okay. We're going to go ahead and balance our chemical reactions, make sure everything is good. 1 aluminum, 1 chlorine, 1 chlorine, 1 chromium, 1 chromium. Everything's good, so it's actually going to be a 1:1 to 1 to 1 ratio. Okay. If I want to figure out the oxidation states or the oxidation numbers, what got oxidized, what didn't get oxidized, we can go ahead and actually do that too. Aluminum's by itself, so it gets an oxidation state of 0. Chlorine has an oxidation state of -1. There is 3 of those, so it's going to have a -3. Chromium is by itself. I don't know the charge of chromium, but I know that I need 3 negatives to balance out the 1 chromium. So this is going to be a +3. Now I'm going to look at what happens on the other side of this. Aluminum is now a +3. Chlorine is a -3. It's a -1, but there's 3, right? And chromium has a 0 associated to it. If I write these out, then aluminum goes from a 0 to a +3. Chromium goes from a +3 to a 0. And chlorine goes from -3 to -3. Nothing happens. I'm not even going to write it down. All right. So 0 to a +3, you became more positive. So if I become more positive, that means I lost electrons. Lose electrons, you are oxidized. Right? +3 to a 0 means that I have started to gain electrons. gain electrons. That means I am reduced. Okay, so in this case, aluminum was oxidized and chromium was reduced in this single replacement reaction. Now, the way we figured out whether reactions were going to occur or not was by using the activity series. The activity series of metals. All right, let's see. We're going to do a quick summary of the things we've talked about in chapter 6 and in this chapter 14. Okay. And then we're going to go back into the net ionic equations, okay? So one was that soluble ionic compounds dissociate in water. Number two, so what does this mean? It basically means like if you have sodium hydroxide solid and we toss it in a container with water, H2O, you're going to have some dissociation. So you're going to have sodiums and hydroxides floating around and some hydrogens floating around inside of this container for your water. Okay. So this is like sodium hydroxide in your water right there. And there's going to be tons of them in there dissociated. Okay. Number two is some ionic compounds are insoluble in water. Okay. So sometimes not everything is completely soluble in our water, right? Like for example, the other one we had the chromium chloride, right? It was aqueous, but the chromium by itself, solid, was not soluble in water anymore. Um, so some silvers, example. So even thinking about that reactivity series, our precious metals are usually not soluble in water, even in their ionic forms. So like silvers, for examples, or gold, they also won't be completely soluble. Number three, solubility rules predict solubility of the compounds. Right? So the solubility rules, what you really want to do is just look into your book. They have a chart with all our solubility rules in them. Use that every single time that you're going to be taking a test. Print some of it out. Have a little flashcard of them. With solubility rules, there's only two things about it. You're either going to look at a chart or you're going to memorize them. That's it. Okay, so solubility rules predict solubility of compounds, right? Quite simple. So soluble means that it's aqueous. Okay. Insoluble is usually a solid. It could also be a gas, okay, or a pure liquid. There's some pure liquids that are insoluble in water. They just float like hexanes. Okay. So not all organic compounds mixed together. You have non-organic and you have organics. They don't normally mesh all the time. Number 4, precipitation reactions. You have two solutions combined to produce an insoluble product. Most of the precipitation reactions will be double replacement reactions. But you will have single replacement reactions that will also do that, like we saw with the chromium metal that got separated, right? That was also a precipitate. And now we're also going to describe some of our reactions using molecular, complete ionic, and net ionic equations. And we're going to retouch on that. It doesn't, but let's see if we could mess with this camera. Nope, the camera doesn't like to be messed with. Right. So I'm going to describe our equations. Using molecular equations, complete ionic, equations, and net ionic. Okay. And last but not least is acids produce hydrogen ions in reactions. So example, if you have hydrochloric acid, when you break it apart in its aqueous forms, you're going to produce hydrogen ions. Okay, it's not by itself. And chlorine. What I mean not by itself, it's not, I meant to say it's not diatomics. It's not going to be H2. It's not an elemental state. It is actually an ion state. So our acids produce those ion states. All right. See if I can pause this and fix the camera. All right, yeah, so let's go into the last part of this, and this is going to be displacement reaction. So displacement reactions, that's just the label that's given to everything we just did. Okay, so all of our work. So for metals, remember, we want to look at the activity series. Okay, usually the heavier you are in the metal, the less reactive you're going to be. The lighter you are, the more reactive you're going to be. Okay, so in case you forget or you're kind of like, I don't remember the activity series, look it up, right? But yeah, the lighter you are, the more reactive. The heavier you are, the less reactive. Okay. So in this case, let's do an example of zinc plus copper, and we're going to see if something happens. So we have zinc solid plus our copper. In this case, our copper is going to be aqueous, and it's going to have a +2 charge associated with it. All right. Zinc is a solid, so it's going to get a 0 charge. We want to know, is this reaction going to happen? Yes or no. So let's look at this activity series. Here's zinc, and let's see if we find copper. Well, I don't see copper, yet I know that copper is somewhere right here on the periodic table, just by looking at the periodic table. So let's see if we have one with copper. Here is one with copper. All right. Just so you guys could see it. Activity series, hopefully it opens. It's taking a while. All right. So we had zinc here and our copper down here under lead. Okay, so copper is actually under lead. You're going to look at hydrogen and go, wait, I thought you said the lighter, the more reactive, and hydrogen's like the lightest thing that we have. Well, hydrogen's a little bit different because hydrogen's a gas with one valence electron and one proton. Sometimes it has neutrons and sometimes it doesn't have neutrons. So the hydrogen that we can see most of the time is regular monoatomic hydrogen, but you also have deuterium and tritium. And deuterium and tritium have 2 or 3 neutrons in it. And hydrogen tends to react with like almost everything. And it just really depends if you're using acids and whatnot. It's just like the exception to that little rule. So just remember that hydrogen's like the exception. All right. Anyways, this reaction will occur. Zinc is on top of copper. Okay, so we know that the reaction will occur. So we are going to get our zinc turning into an aqueous plus our copper breaking out of this solution that it was in. So remember, there's water in this solution, but we don't have to write it down. When you start writing in your water and everything in there, it gets more confusing, okay? So you don't want to confuse it. So we're going to have a +2 charge with that one and a 0 charge with this one right there, okay? If we want to balance them, 1, 1, 1, 1, okay? Let's go ahead and create our Leo-Ger thing. So remember, when in doubt, write it out. Leo-Ger. All right. Lose electrons oxidized, gain electrons reduced. So zinc goes from a 0 to a +2. And copper goes from a +2 to a 0. So this becomes more positive, and this becomes more negative. So more positive means you lost electrons, which means you're oxidized, right? More negative means you gained electrons, which means you are reduced, okay? When you write your half reactions, you are going to write half reactions like this. Zinc 0 turns into a zinc +2. So it's the same thing that we were doing here. The other thing is that you also want to indicate the states that they're in. So this one is a solid, and now this is aqueous. Okay, so that would be the half reaction, and you indicate that it's oxidized. And you would do the same thing for your copper. You would say, all right, copper started as aqueous, and then copper turned into a solid. And this is charges right there. And then you would write down reduced. So this is the actual proper rate of writing half reactions. Okay. When it comes to redox. So it says, what is the redox half reaction? So redox half reactions. It's these ones that we've been doing to figure out the oxidation states and the oxidation numbers for them. One of the things that we're also going to add, so this is like adding to our half reactions that we hadn't done before, but we need to now start taking accountability of it, is what happened to those electrons. The electrons moved, but they went where, right? So here, the electrons were part of zinc. Here, the electrons left zinc. So where are those electrons? So in this reaction, I'm going to have this plus 2 electrons. Okay, so the 2 electrons are on this side. They were produced in this oxidizing equation. Here I have 2 electrons out in the wind and then a 0. So where did we gain those 2 electrons? Well, from here. Those 2 electrons came from there. So 2 electrons plus copper with a +2 charge is going to equal copper with a 0 charge. So this was reduced. Okay, our electrons are on the on the reactant side, and here our electrons are on the product side. So now we're just including the electrons. If it was a +1, then I would say +1 electron. If it was a +3, I'd say +3 electrons. Okay, so let's go into reactions of metals with acids. So in the reactions with metals with acids, not all metals react with acids. Okay, not all metals react with acids. Precious metals do not react with acids. So precious metals. And precious metals all are silver, our gold. Those are considered kind of like your precious metals. Let's write those down. So we're going to have silver, gold, platinum, and some copper sometimes, right? Copper is more reactive than the other ones, but I'm going to put it in the list. Most reactive metals react with water to produce metal hydroxides. Water to produce metal hydroxides. Okay. And not just the metal hydroxide, but they're also going to produce hydrogen gas. And hydrogen gas. So they're going to produce a hydroxide and hydrogen gas. Okay, so those two things. Right. Let's do an example of that. So we're going to have calcium plus our water. Okay. In this case, we're going to get calcium is going to react with the ionized form of our water, and we'll get calcium hydroxide plus hydrogen gas. Okay. Now, hydroxide came about from the dissociation of our liquid water when calcium was introduced. And that dissociation occurred because calcium is reactive. Okay. And by looking at the solubility chart, I could see that hydroxide is insoluble. Calcium hydroxide specifically is insoluble, and that's going to just create a solid. Okay. Let's look at a solubility chart just so I can show you guys how to read one. Okay, so I'm just going to Google a solubility chart. I'm going to go to my images really quick and then find one. Opening tab. Oh, it's sticky. Really small, we can't see that. So let's do another one. All right. They are like not popping up the way we want them to. All right, well, we could also look at the solubility chart, the rules. So here is like some rules. we're looking at hydroxide. It says hydroxide ions that form insoluble compounds. That means they do not dissolve inside of or ionize inside of our water. And that's going to be a hydroxide group. And it says the exception is when combined with group 1 ions or ammonium. So you could combine it with group 1 ions, calcium, barium, strontium, so those ones, or ammonium. So any of these are your exceptions for it to be soluble. If it's not combined with any one of these, it's going to be insoluble. Now, like I said, people have made songs and everything to memorize the solubility chart. All right, that's like honors advanced placement. I don't know. General chem, you will have to memorize them, but not from my class here. But anyways, you're gonna have a solubility chart, and let's look at this one right here because it's clear. Okay, the way you're gonna read it is you're gonna see what it's combined with. So I'm gonna look at calcium hydroxide. My cations are here. Here's calcium. Now I'm gonna look for hydroxide. Bing, 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 bing. There's calcium hydroxide. All right. So calcium hydroxide has this little SS. I'm not actually quite sure what that SS stands for because I've never seen that SS. So maybe it's partially soluble. Not quite sure. Let's look at another one. All right. Calcium. And let's look for hydroxide. There it is. Calcium, slightly soluble. SS, slightly soluble. Right there. Okay. So you could do one of those two things: look at the rules or look up a solubility chart, and both of them will help you out where you need to go. Um, Okay, the last thing is I just want to retouch on the molecular net ionic equations, but I think I'm actually going to do that on the little practice worksheet that you guys have. I'm going to go through a couple of these and we'll kind of figure out what our net ionic equations are. If not, refer back to chapter 6. We actually cover those in the end of chapter 6. All right, guys, take care.